doctoral student, right?
Right.
At the group since 2020. And as a matter of fact, he already did his bachelor and master's thesis at the same group. And in his talk, he will talk about cavitation bubbles and how he analyzes them using the advanced possibilities of a free electron laser.
Thank you very much. Jung, could you unshare? Then I could share my screen.
Okay.
Can't see it yet.
Somehow I cannot. Okay, one moment. Okay, good. Is it okay, right?
Yes.
Okay, perfect.
Do you see the full screen now?
Yep.
Yes.
Okay. Okay, yeah, thank you for the introduction. And of course, I'm really happy to have the opportunity to speak here and to share our research of laser-induced cavitation dynamics with single free electron laser pulses. So we are dealing with cavitation here, and the term cavitation describes the emerging of a cavity. In our case, that's gas or vapor bubbles in water, and this has been researched over 100 years already, starting with boiling processes in a kettle, but it can also be induced by a laser, and that's what I will focus about here. So if you focus a short pulse and intense optical laser in water, you generate optical breakdown. This means a plasma is generated, and this plasma expands really rapidly, by that compressing the surrounding water, and this generates a shock wave. As the plasma then grows further and cools down, the ions recombine and the gas or vapor is formed. This is the bubble, basically. It's still very, very hot and high pressure gas, and hence continues to expand very, very fast. You can imagine this basically as a small explosion underwater. And the whole process can be followed by, for example, optical high-speed photography. You see here in the first frame still the very early process, so the plasma spark is still visible. But the bubble will expand up to a maximum radius, which could be at 50 microseconds later here, and afterwards will collapse again. The whole research is, of course, motivated by many applications that have been developed in the last decades, from medicine, like, for example, laser eye surgery, also chemical processes and material science, such as surface cleaning processes and so on. But it's also, of course, fundamentally very interesting to investigate matter being driven to extreme states, like the transition from a plasma to hot gas, or the highly compressed water inside the shockwave. And that's what we are focusing here. So the very early time scales after optical breakdown. And I'll be mainly talking about X-ray holographic imaging, which is a full field imaging technique. You can already see here a sneak preview of our results, showing the time evolution by the X-ray holography. I will show you that this is a high resolution technique with unique quantitative contrast, and that it also can yield 3D structural information. And then I quickly will follow up with a second experiment, which is time resolved wide angle X-ray scattering of the same process, where we investigate the molecular structure and the molecular dynamics. So the experimental setup at the Materials Imaging and Dynamics beamline of the European XFEL looks basically like this. We focus the X-ray beam with nanofocusing X-ray lenses to create a divergent beam. And in the defocus at some distance behind the focus, we generate the cavitation bubble inside the water chamber. Let me switch the marker here quickly. So here in the center, the cavitation bubble is sealed by the nanosecond optical pump laser. And the X-ray hologram is then formed by free space propagation and recorded with the detector in a distance of a few meters behind the interaction region. The whole experiment is conducted in a pump probe scheme. So we record the dynamics by varying the time delay between optical pump and X-ray pulse, and we seed a new cavitation bubble for each arriving X-ray pulse here. You see here again a time series of X-ray holograms of these cavitation bubbles. In the top row, this is still the flat field corrected hologram, while on the bottom row, this is already a two-dimensional phase reconstruction. So for holography, you always need a second step, which is the phase retrieval, and this is here numerically solved. I cannot go into too much detail here, but I want to stress that this is already quantitative data. So the projected phase that we retrieve here in the sample plane is anti-proportional to the mass density of our sample here, which is the cavitation bubble. And in the center, the positive projected phase corresponds to the cavity that has already formed. So it's less dense than the surrounding water, while the dark region around it is the compressed and high dense liquid water. For the analysis of our whole data set, I want to switch now to a reconstruction scheme that has been reduced in dimensionality and is working with a forward modeling approach in radial coordinates. I want to quickly mention that this can also be used to study low contrast and small structures like single lipid bilayers. And with this reconstruction scheme, one can retrieve, for example, the distance between the monolayers here by forward modeling the fringe pattern. So the analysis scheme for our cavitation events now looks like the following. From the two-dimensional intensity pattern, the hologram, we calculate the polar average and retrieve here the radial intensity pattern. And the measured signal is here shown in the red dotted line. And we compare this with a numerically propagated a signal, which is propagated between the sample and detector plane. And it's basically a fitting algorithm reconstructing the phase profile in the sample plane, which is shown here on the right. So this is again in radial coordinates here, the projected phase. We can do a next step here by again using the spherical symmetry, or at least elliptical symmetry of our cavitation events, and perform a projection inversion step. And by that, we can really retrieve the 3D radial phase profile, which is also, again, anti-proportional to the density profile. So here on the right ordinate, already the mass density is plotted. And you can see the different regions here. In the center, there's basically the cavity, the bubble has been formed. Then we have a region of shock compression with densities up to 1.4 grams per square centimeter, cubic centimeter, sorry. And beyond the shock front, of course, there's equilibrium water. This analysis scheme has now been applied to roughly 10,000 single-shot X-ray holograms. And I show you here exemplarily some phase profiles for 2, 3, and 7 nanoseconds. We can follow the phase and density profile over the whole profile, and the dynamics of this growing bubbles and shock waves. And we also see that looking at the color scale here, which represents different bubble energy for each event, that, for example, higher energy events propagate faster and, of course, also have a higher contrast. The next step would be to, that we applied here, is assuming an equation of state for liquid water. And by that, we can relate the density profile of the shockwave to a pressure profile, actually. And this is shown here on the bottom. It's now the pressure given in gigapascals plotted over the radius for different exemplary shockwaves only here. And we can compare that with hydrodynamic simulations. And our main results are that basically for the low energy events, we can reconstruct our experimental data quite well with the hydrodynamic simulations. However, if we try to fit our higher energy events, here different experimental curves are shown with the hydrodynamic simulations in red, we observe distinct discrepancies. Most importantly in the shape, so there's a different slope of the shockwave profile, but also in terms of peak pressure. And we believe that this is due to our hydrodynamic model, of course, which maybe cannot describe all the details of this complex process here, but most importantly also due to the equation of state that we assumed here. This means that we need to understand better what is actually happening, how does water behave under these high transient pressures. And this directly motivates our follow-up experiment, which was also conducted at the European XFL, the same beamline, which is time-resolved wax. So we basically conducted the same pump probe experiment here, measuring the scattering signal inside a water jet. And what we measure here is the characteristic water peak, which corresponds to the mean distance of the oxygen atoms in water, which is here usually found at around 2 inverse angstroms. We observed that in the first 10 nanoseconds after our cavitation bubble has been seeded, this characteristic water peak actually shifts in its position to roughly 2.5 inverse angstroms. And while we cannot fully retrieve the structure factor here due to the limited detector size, unfortunately, we can still attribute the shift in peak position to a conformal change of the water molecules from a typically tetrahedral arrangement of liquid water towards the structure of a more simple liquid. Okay, thank you. I'll finish quickly. Yes, so basically that also already brings me to my conclusion. I showed you a time-resolved single-shot X-ray holography experiment with a reconstruction scheme in radial coordinates. We compared our results to hydrodynamic simulations and also investigated the time-resolved structure of water during this process. As an outlook, I want to mention that we can really perform this X-ray imaging experiments in a correlated way with the scattering and thereby can directly compare this effect from 2 perspectives. We also, in very recent beam times, investigated the interaction of optical femtosecond lasers with water, and also investigate the collapse of acoustically trapped cavitation bubbles, which are periodically oscillating. So I want to acknowledge and thank, of course, everyone who was involved in this project. And with that, thank you for your attention.